Alright everyone, we are back and we are going to do our problem set 6 solution video. So we're going to complete a unity feedback control for this biological chemotaxis process. So I really like this as an example in our system. And let's go ahead and let's first sketch out this, and it goes to our air, and then we have, let's get this minus here, it goes in, let's say this is sensor, and then we have getting into here, and this is our Y. Actually, excuse me. Let's go ahead and get out of here. So let's go here. This is our Y. It goes down. We'll have our plant, and then we'll have our, and then this is our, oops, I'm running out of room. I'm going to call this my, actually here, let me just kind of erase that for a moment. So let's go here. Then I'm going to put this as our plant. I'm going to put this as our, controller C. This is our U, and then that goes to our, I'm going to call this A for our actuator. So, and you know the figure that we're trying to do. So let's read this system. So E. coli performs chemotaxis, sensing chemical gradients, adjustments, rental motion. So the idea here is, let's say you have an environment, and let's say there's a lot of chemoattractant over here, where the cell is basically going to move along this gradient, and it's going to move towards this general direction. So my cell is here, it's kind of sniffing this gradient, and it's going to move towards where there's like a kind of a gradient in the concentration. So receptors detect the attractant concentration, signaling network process the input, the flagella motor generates the movement, bacterium biases its random walk to move towards the highest concentration. So if there's no gradient, it's just going to kind of do what's called run and tumble, which is just kind of a random walk. But if it senses it, it starts to kind of become a directed, basically transport process. E. coli does not naturally respond to this, so you can treat this as the environmental signal. So let's go ahead and let's break this down. So I think the key, one of the things I think that's fairly straightforward to, what's the sensor in this system? Well, the sensor is basically, we're sensing essentially like that chemoattractant using our chemoreceptors. So it detects those changes. So those chemoreceptors are our sensor here. What about, so let's kind of work from there. So our reference is going to be what? You know, basically we want to move towards like the higher concentration. So higher concentration. So we always be, essentially in this system, we always want to be, we want to be increasing essentially. We want to move to the highest concentration in that system, right? So we take that, the air is just going to be the difference between, kind of the more attractant versus what we actually sense, the Y, right? So air is always going to be that, you know, R minus Y. And that Y effectively is basically the chemoattractant. It's effectively the chemoattractant that we're sensing, you know, along that trajectory, right? So as we're moving, we're sensing that, you know, concentration, and we're basically comparing that current concentration along that trajectory to the reference. And the air will then send us a signal to our controller. And our controller in this system, what would it be? Well, it's our signaling network, right? So this signaling network is processing that air input. And then it's going to send a command signal to our actuator, which is the flagella motor. And then the plant is essentially like all the biomechanics that go into, again, adjusting, moving your trajectory towards, you know, that kind of next higher concentration. So there's lots of ways you can kind of analyze this, but I think it's a cool system. You can kind of sense of how this feedback is kind of integrated and how the bacteria responds. So that's your problem 1. And I'm looking forward to some very fun answers to that problem. All right, so now let's look at the following system equation motion. We have a mass, it's going in this direction. We have basically our equation of motion for the system. Wasn't I so nice? And we're also told some other factors as well. So I'm just going to move this over here. So we're told in this system that our K1 is 15 Newton meters, K2 is 35 Newton meters, our damping coefficient is 4 Newton second inverse meters, our mass is 10 kilograms, and our input response U of t is essentially going to be equal to 1. So we're being asked to calculate the transfer function of the system and the time response, essentially, of that system. Well, we know we want effectively our output, which is going to be x of s, over our input, which is u of s. So we need to kind of get to this expression. Now, we can almost by hand, because if it's a double derivative, it's going to be m s squared plus b2 s plus k1 plus k2 of basically nothing. And then that's going to be equal to, now, when we look at u, and actually, if this is basically going to kind of be all in terms of, so this is our x of s. So if you have kind of the transfer function, in front of that, you're going to basically factor out, these values. So this is our output function here. And we're to divide that by, or actually we're going to set up that ratio of that input function. Now, if our input function is 1, we can actually do the Laplace and actually find that ourselves. So let's go ahead and look at it here. So if I have, this would effectively be, and remember, when we're taking the Laplace transform, we're going to set this, the initial conditions equal to 0. That was kind of one of our, effectively our tenets of what we're looking at here. So you can see we can factor out all these different kind of parameters when we run that Laplace transform. So there's an x of, basically, I did a kind of shorthand here. There's an x of s multiplied by everything here, effectively. And that's important in a second. Our u of s, if our input time is 1, Laplace transform will be 1 over s. So here, this is 1 over s times u of s. And so now we can basically move that function over. And if we want the transfer function, it's just going to be, effectively what we're dividing by. So we're going to move that one over, x of s, and we're going to actually get 1 over, basically, because if we have that 1 of s right here, you can see Laplace transform, actually we can do u of t, which is equal to 1. I wonder if I can, I'm just trying to set this first. I'm just playing around here for just a second. Exactly. So we'd actually have, apologies for that jump, but you can see we just kind of protected our transfer function here, so it matches. We can look at our time response, and we can kind of see what we're looking at. You can look at different length scales. We can do plot range. And that seems to kind of be, if you think about that system, the response doesn't look too, insane. Fantastic. What about, now for the spring mass density lecture, do the same for a different input. So if we were to look at this input here, all we would do is just take this times, again, we're just moving this over. We're going to multiply that here. Oops. Just taking the transfer function. Then we can just set that all 1 divided by everything here. Is that all correct? I'm going to call this, LT1. I'm just going to do 1 divided by LT1. Excellent. Yeah, that looks correct. And then we can look at our transfer function here, and then we can get the following. So similar. Plot range all. And actually, let's look at it. Let's look at 52. So you see more kind of, it's always good to kind of like look at the response. The oscillations kind of go a little bit further. It makes sense because it's a sinusoidal function. But again, we're going to develop some tools in a bit. Fantastic. Now, for the spring mass damper system covered in lecture, consider a mass of 3 kilograms, a spring constant of 15, damping coefficient of this, with Dirac delta command input. Take the Laplace transform, create a Bode plot, and common behavior of the system. So we know our great friend, spring mass damper, ms squared plus b s plus basically k is going to be equal to our input. If it's a Dirac delta function, we should know Dirac delta, let's say in function of t, if I try to do the Laplace transform t with respect to s, I think that's the language, it just becomes unity. So if I do my transfer function, it'd be x of s over the input u of s, which is just going to be equal to 1, so that'll be equal to 1 over, again, these friends that we've seen before. So our transfer function would look something like this, except not 1/8. It's actually a mass of, the mass is 3 kilograms, that's m. The damping coefficient is 2.5, and then we're going to have a spring constant of 15. So we'd have this. We can look at our Bode plot and our, basically, the responses essentially of those functions. And we can see, again, you get kind of that resonance peak that you would expect, essentially, from this spring mass damper system. So looks pretty good. Fantastic. And then finally, calculate the transfer function for this block diagram. Unity feedback, we kind of essentially know what that system is going to look like. And we've derived that actually in class. But again, actually, we derived that a lot in our class. So you can look at those relationships. And all we're doing is just plugging and chugging and setting our controller to this, our plant function to this. And if we look at the output y over that, basically the input of our function, we'll have this as a result. And we can do, let's see if we can full simplify. And that's our transfer function. That's problem set 1 in the books. So thanks, and we'll see you next time. Bye. Or problem set 6, excuse me. Bye.